Again, this is the recording for the October 22nd of Lab 9. Lab 9 deals with the basically electrical circuits. For those who are sitting in Physics 10, that will not be covered until sometime, not even next week, the week after. So we are ahead in terms of the lab versus what we're doing in the lecture. That is expected because the labs are only several topics, and whereas the lecture covers a lot of topics. Right now, we just finished thermodynamics. We're moving to waves. The last week's lab in Physics 11 was waves, and today, to next week when we start waves, we will start also electricity next week, but we will not get actually into the currents, the DC currents, until later the week after. So we have quite a bit of time before reaching there. I'm hoping that the introduction of the concept that we will cover in this lab will be enough to do the activities, to understand basically what the current is, to understand what the resistance is, and to be able to do the measurements and actually the calculations also that go with it. So if you guys don't have any questions about the previous lab or anything that is coming, let me share with you the instructions for the lab themselves, first of all, from Canvas. This is similar to a previous lab where we had the instructions and also an Excel file. The purpose of the Excel file is twofold. First of all, it's going to regurgitate for you data. It calculates some stuff that you will need. I mean, short of having to do it manually, which can be time consuming and can lead to some errors, is going to give you those values. So you need to take your data from your table to the Excel file, where it's going to give you the missing data that you need to put back in your table. That's one thing. The other thing also is going to generate graphs for you, okay? 2 graphs that you will need as part of your lab report. So it's going to automatically do that. You don't have to do anything. All you have to do is put the data in there, okay? So you have 2 options for this lab, and that's basically what you need to mention today's discussion. Either you actually do the calculation manually, and I will show you how you do them, and to actually draw the graphs, and I'm going to show you how you do them, or just do the Excel file, okay? So those are the 2 options, okay? So that's basically the one thing that I needed to mention. The lab is due next Friday, just like now we've been doing now for quite a bit. So the lab is due next Friday, and again, the stuff that is there from before. So I'm going to get to the lab instructions very quickly. But before I do that, again, a reminder of how this labs are grading. This lab turned out to be graded out of 89 points. This is the rubric. You will get a full credit for your name and that of the name of everybody who worked with you. Just make sure you have that. Also, the objective, it's a good practice usually not to start with the objective, especially in this lab more so than the before, because you need to understand what's going on before you put it in objective, okay? And then you need at least 2 sentences or more, otherwise you lose points for it. Then we have the tables. We start right away after the objective with a big table. It has 52 points because it has 52 entries. Some of these entries, you need to calculate them. Some of these entries, you just transcribe the data from your observations. And if you miss one or more on the entries, you're going to lose points depending on how many miss. If you don't do anything, you're not going to get any credit for it. Then you have several questions, typical of things that we've been doing in here. And the point that I wanted to get to is this one in here, the Microsoft Excel file that I already added to you guys, which is this very same file that you see in here. If you have it filled correctly, it should do 2 things for you, as I said. It should give you data to complete back your table 1. That's one thing. And it should also give you the graphs you will need. So that is option 1. Option 2, you could do it manually too, okay? So that is the 2 options. That's what I want you to make sure that you're aware of these options that you have in here. And then you have typical questions. Now, question 2 is actually related to table 2. I'm sorry, is related to table 1. So you really cannot do table 2 unless you do table 1. So that is something that you have to be aware of, because it prepares you really for the conclusions, for what the next questions, and then the conclusion, typical on how grades for the conclusion is. Any question about the rubric? Guys, don't have any questions. I'm going to open this thing in here. Oh man, I don't mean to do that. I want to open it with Adobe. And then stop sharing that screen and come back to it here. So this is Ohm's law. This is lab 9. Basically, this deals with electricity, electrical currents. We have two kinds of minerals. We have two kinds, I'm sorry, not mineral. We have two kinds of material. Materials that conduct electricity well, and materials that don't conduct electricity well. The ones that do conduct electricity well are like, for example, gold, silver, and copper, and iron, and some other metals, like, for example, aluminum and things like that. In industry, in your house, most likely you have copper. I mean, you have to be super rich to have silver or gold for your wiring. That is not smart, okay? They're better conductors though, but in industry we use copper because copper is cheap enough to have, and also it's a very good conductor, okay? It's not the best, but it's very good. Iron is the worst among the things I mentioned already. Other materials that don't conduct electricity well are, for example, like plastic. That's why we use it to wrap the wires with it so that we don't get electrocuted. Also wood, also air is those are insulators. So that's basically in terms of conductivity, in terms of electricity. So you have conductors and you have insulators. We're going to assume in this case that we're dealing with conductors because we want electricity to be conducted. Okay. Electricity when it's going, so basically I have a battery of some sort. I don't have a battery in here with me, do I? Sorry, I don't have. I must have it, but I have so many things in here that is probably buried under many other things. Anyway, so you have a battery, which really it's the role. So let me draw a circuit for you guys, especially since we didn't do this in class yet. So let me stop sharing this screen. Let me prepare this screen for you guys. And this is physics 11. So let me come in here and share with you this screen. So what we have usually, we have a battery. So I have a battery. A battery, what it does is it provides a difference in potential, that's all, okay? It pushes charges, pushes electrons from one side to the other. It's connected to something, like for example, a light bulb. A light bulb in this case, which is like this, has filament in here. This is a resistor really. And then usually we have a switch. You know the switch that you have in your house? Where is my switch? The switch is actually outside. Is it outside? I think it's outside. Switch, okay? So when it's open like this, there is no current flowing through the circuit. And then we close back to the battery, okay? So in the sense, in this situation, I don't have any current flowing. When the switch is closed, meaning this wire is closed like this, then current starts to flow. Charges start to move. And when they do, in this case, they hit the resistor, and because of the resistance of the resistor, meaning that there's too many collisions in there, this starts to warm to get to a point that it starts to glow, okay? That is what a light bulb is, okay? Then after that, the charges will continue. The minute they hit the other side, so there are two sides to the battery, a positive side and the negative side. When a charge comes into here, it's going to be carried by the battery to the other side. And now it's on this side, finds itself in here, so it's going to continue. Let me draw a similar things with something that is probably more familiar to you guys, at least can drive the point a little closer. Let me give you an example of bunch of students, let's take 10 students, for example, they went to a ski resort, okay? So here is the mountain. Let's assume that there are a bunch of trees in here, okay? So this is the equivalent of the resistor, okay? So let's take 3 trees in here in this case. So the students, they are here, and then they go on their skis. At this point, they're just moving around freely. The minute they hit a tree, of course, they bounce back, they stand up, then they move back, they hit a tree, they basically fall to the ground, then they get themselves ready. Of course, that leaves bruises and things like that. Of course, depending on how many trees in here, there is going to be too much headache in here. But at the end, they will come down. Okay. Now they are on the ground level. How many students do you think will end up on the ground? If 10 of them come from the top.
All 10?
All of them. Yes, very good. I mean, we're assuming that, yes, they will suffer bruises and bumps, but at the end, they will make it down. Okay. And the reason why I'm saying students because I don't ski. Okay. So they're all 10 of them, they will be down in here. So if all of this is what you have, that's basically the end of it. You don't have anything else. So all 10 of them are in here, and that's the end of the story, really, if that's the case. Now, if the 10 of them will travel this way, there is no energy expense because there is no height in here. So there is no skiing going around. Once they come in here, for example, assume that there is a lift in here, elevator. They all come in here, they go to the elevator. Now the elevator takes them back up in here. So this is your elevator. This is equivalent to the battery. So the elevator role in here is that if it finds students wandering around in here on the bottom, it's going to take them up, okay? Once they're up, they will find themselves going through the incline in this case, bumping into the tree in here and so on and so forth, okay? So in this situation, I have these trees that slow down the number of students, okay? The 10 students. This is equivalent to the light bulb or the resistor. Let's say, for example, I have a bunch of other trees in here too. How many trees do I have now altogether? So I have this resistor 1 and this resistor 2. How many trees do I have altogether now from this graph in here? I didn't hear anything.
I mean, it looks like 8 trees.
I think these are 3.
Oh, 3.
And this is 4.
Oh, 7.
7. So you see in here now the resistance has increased. So the ones who came in with a little bit of bruises, now they will have more bruises. Do you guys understand that? Because not only they will come through these trees, but they again have to go through the second trees in here. So these trees now they're in series. In other words, after the 10 students bump into the first bunch of trees, then they come out of it, okay, probably with a little bit of headache, but then they will go through the second series of basically of trees, the second bunch of trees, and then they will come at the end 10 students intact. Do you guys understand that? Yes? This is an analogy.
Yeah.
And the battery now is always played by this elevator. The elevator role is this. Once it finds students on the ground, it's going to grab them, drag them, and put them back up, okay? They probably don't want to do this anymore. You know, once you go once, probably you want to stay in here. That's what you want to be, okay? But screaming and shouting and all of that, the elevator would drag them and push them back in here where they find themselves up. So they have to go on the incline again. They have no choice in this case. And then they go through the resistors again. And as long as the elevator is doing its job, these students will always continue this circuit. You guys understand this? This is an analogy 100% to the circuit up there. This configuration of trees in here is called in series. And in a series configuration, the resistance, as if I have, instead of 3 and 4 bunch of trees, I have actually the sum of both of them. So the resistor, in this case, the equivalent resistor, as if I have one bunch, I have one bunch of the sum of the two resistors. I have the equivalent, as if I have them all grouped in only one bunch, which is in this case 7. So this is that analogy. Let me give you another scenario in here. Okay, I have the same elevator. So this is your battery. Its job is one thing. Okay, as long as it has energy, it's going to drag any student and put them on the top floor. Now, once they find themselves in here, they're going to split. But now this is the thing with it. Okay, let's say, for example, the height in here we're talking about is 10 meters. That's a very high mountain. Okay, so this height is 10 meters. Okay, so the elevator can grab a student or students and take them all the way to 10 meters high. It cannot do more than 10 meters. That's it. Okay, so this elevator also is doing the same thing. So this is a 10-meter height. Now the students have to come down. Now they actually there are two ways of going around. Okay, there is one way going like here, one route here, where there are only 3 trees in this bunch, and the second route, which is parallel to it, where are the other 4 trees. Okay, and at the end, the 2 routes will meet, and they come down again to the floor. So the students, 10 of them are coming in here. How many students do you think I will have at the end and the bottom? After they go through the 2 routes, how many students I will end up in here?
Well, still 10 of them?
Still 10. Very good. I don't have, I can, I mean, I assume that all of them survive this thing. Okay. I know I'm traumatizing students, but okay. So now the question is, do all 10 of them go through this bunch, R1, or all of them go through R2? What do you guys think? Which one is easy for them to handle? Through the 3 trees or the 4 trees?
The 3 trees, so yeah, R1.
So more students actually will end up going this way than on this way, because this is easier than on this side, which is a little bit harder. More resistance on this way than in here. You guys understand? But all of them, the bunch that go here and the bunch that go there, have to descend the 10 meters nonetheless. Okay, both of them end up with going the 10 meters nonetheless. I can actually tell you how many fraction basically of students will go in one way and the other way, assuming that I can split students in fractions. So this is how many they will go. Since this descent is 10 and requires 10 students to do it, so it's 10 divided by basically, what is it? 10 volts divided by, so this is the equivalent of 1 basically, 3. Okay, and I'm oops. So, oh man. So since I did it in these proportions, I can tell you that 4 students will go here. No, not 4. What is it? The ratio of 3? I can tell you what the R equivalent, and from that I'm going to. So the R equivalent in this case is a little bit more complicated, but this is the formula for it. It's 1 over R1 plus 1 over R2, and that is 1 over 3 plus 1 over 4, which is the common denominator is actually 12. And I have here 7 over 12, that is the ratio. So it's 12 over 7, the ratio of the students. So 3 times 12 over 7 will end up in here, and 4 times 12 over 7 will end up on this way, and 3 times 12 over the other side. And at the end, I will have basically split your students piecewise. so that they can end up at the end 10 students. Here's the thing to remember. Forget about everything I was talking about in terms of that. The equivalent number of trees follows this relationship. Okay, just take it as a rule. Okay, there is a proof for it. We're going to discuss it when we do the class. Okay, so this is the equivalent resistance in this case. The point to take from this analogy, the second one, is the fact that students actually split, not necessarily evenly, depending on which way is easier. The easier will have more students go to than the harder path. Fewer students go to the other side, but at the end, the 10 students will be recovered. Okay, so this is an analogy of the battery and the incline. But at the end, I will have my 10 students, all of them fully back, basically intact. As long as the battery does its job, a 3-volt battery, for example, or 1.45 battery, there is a potential drop in here of 1.5, just like the height I was talking about. Okay, the 1.5 battery that you get from the store, the AAA or AA, can take charges and make them, they want to be here actually, the charges, and make them rise again 1.5 volt. Now they want to fall the 1.5 volt through the incline, going through the resistor, it warms up, and then they follow. Now they have fallen completely to the ground. The battery's role is similar to the elevator. It's going, once it finds charges on this side, it's going to move them to the other side. Okay. When we do the lecture in Physics 10, we're going to talk about the process actually being a little bit opposite, because by weird convention, we came up with the electrons being negative. Had we chosen the electrons to be positive, this picture would be beautiful. There is no problem with it. But in actuality, it's the electrons moving in this direction actually, and going through the resistor and coming back to this side. So because the ions are positive on this side, and the charges that are negative in this case, so once they descend, they come in here, they're fine. They cancel one another. But the battery has energy. The battery will drag the electrons. And as a matter of fact, if you look at the electrons, they will not want to be next to this electrons. It's already negatively charged, so they don't want to be there. They want to stay in here. But the battery will drag them against their own will and basically put them in the opposite direction using something called the chemical process. Usually there is chemistry in here involved. Okay, so it has some force, which actually called the electromotor force. Okay, that is an energy. How much is the electromotor force? It's exactly the power of the battery. Okay, in your household, when you look at it, you have 120 volts. When you connect it to when you connect your computer, for example, or TV, the charges will move from the side that is negative, but let's assume that it is that is the convention that we took. The charges, the charge carriers will move from the positive to your computer, come out from the other end, and now they are happy. But again, the power company has made sure that you have 120 volts, so it's going to drag them against their own will and put them on the other side to maintain that 120 volt. Once they reach that point, then they go again through your device, whatever, TV or computer, and they're happy. They reach their point where they need to be. But again, the power company makes sure to maintain 120 volt across its ends, both ends. So it's going to drag those electrons and put them on the opposite side, and the cycle continues until you unplug your device, or the power shuts off, or the power company runs out of energy, or your battery dies in this case. Okay, so that is in a nutshell what the circuit is. Okay, it's all of it has to do with the electromotor force. As long as you have an electromotor force in the battery, at that point you decide to go, you know what, the battery is dead. It does not do 1.5 volt as I purchased it and I wanted to. My light in here is dimming, and actually it stopped now from being glowing. So I'm going to go to the store, cough up more money, basically pay whatever they ask for it, grab another battery and put it in the circuit, and the whole cycle now goes again and again and again and again until the battery runs out of energy, in which case you have to go and pay for it one more time. So that's basically how the electric circuit is, and the analogy with the elevator is similar in a sense, because the height in that case is a physical height. The height in this case is actually a potential, electrical potential, whereas the other one is a gravitational potential. Okay, and the electrical potential in your house is about 120 volts, unless you're dealing with a device that requires higher potential, like some of the uh, dryers and some of the other heavy machinery that requires 240 volts. But that is typically what the voltage is. Any questions about the concepts, more or less? For those who took Physics 10 before and they are fulfilling their requirement for Physics 10, taking Physics 11 now, did you remember this discussion that you guys had when you had electrical circuits? I don't know if any of you them are in here. Anyway, it looks like all of you guys right now are Physics 10. So let's continue with this discussion then. The instructions. The main thing to remember in here, the voltage is related to the current via this relationship. Depending on the length of the wire, depending on the type of the wire, depending on the cross section of the wire, it has specific resistance. Okay, and that is given by R. Resistance is measured in ohms. So this is measured in ohms. So R is measured, and the symbol for ohms is capital omega, by the way. Okay. I is a current measured in amps, in amperes, and V is the voltage measured in volts. So this is an ammeter. Oh, the light is. The A on it stands for ammeter. Let me see. Do I have other things in here? Hold on. Let me grab my my bag in here. I think I have voltmeter too. I got this from Amazon the other day. Okay. Here is the voltmeter. Okay. So the current in here, okay, the current in here, this is first of all the ground. And then you have two inputs in here depending on the gauge, because this one is gauged from 0 to 3 volts for low current from 0 to 3 volts. Okay. I don't know if you can see this or not. And the bottom scale, 0 to 3. And the top one is from 5 to 15 volts. So depending on which one you're using, if your voltage is low, you use this one. So the battery that I was talking about, 1.5 that I get from Walmart, I will have to use this one in here for the middle one. Okay. For the high voltage, I have to use the other one. Okay. Same thing with the ammeter. The ammeter measures the currents, and it also has two. It has also the ground. In here, the black one is the ground, and it has two scales also. You have low currents, in which case I use the middle one, and then it has the high current, in which case I use the top one. This one can measure technically up to 3 amps, and from currents from basically 0 all the way up to 0.6 amps. Okay, but it allows for the current to be in the opposite direction. And I happen to have a lot of things in this thing in here. Next week we're going to be doing the motor, and this one has actually a motor in it. It's kind of fun. This is not an expensive kit. If you guys can get to this one, I think I paid for it like $40 or something. It has everything. It has a lot of fun stuff in here. Okay, because I don't have access to the labs anymore. So this is basically short of doing that in the labs. This is what I was talking about in terms of a switch. This is called an AB switch, actually. This switch you can take this one right now. It's an open on both sides. I can close the circuit in here if I have two wires connected. Oops. Yeah, connected to this side because I closed it in here. If the wires are connected on this one, it's on the other side. This is called an AB switch because it can be in position A or position B. Right now it's in position B. there is another type of switch that you can have, which is the regular switch that I was working with earlier. So you have a wire that's connected to the ground on this side, and you have a wire that is connected to the live wire on this side. And this is now it's open. Once I close the switch, the current will flow on from end to end right now. Okay, so this is how switches work. This is a normal switch, and I have a bunch of switches in here and other things also around. Anyway, so this is a night kit that, let me put this thing back in here, for the voltmeter. So assume that you have a voltmeter to measure your voltage, the one I was showing you, okay? And assume that you also have an ammeter to measure your current. From this point on, now you have V and you have I, okay? The resistance is going to automatically be in ohms, in honor of Mr. Ohm, where this law is named after him. This is Ohm's law. This law is named after Mr. Ohm. Now, the potential, the electrical field and the potential are related to one another via this expression. You're not going to need this expression, okay, for this lab. This expression actually also is relating, I told you that it depends on the material, okay? This is the resistivity of a given material. For example, for copper, is it one, I don't know if it's one, I think it's 1.47. Can I put, I'm trying to put a decimal point in here, okay? And this is not allowing me to draw a decimal point. So this is a decimal point. Times 10 to the negative 8. Ohm meter. So that's for, I can't do a decimal point in there. I can't put a point in there. Anyway, this is copper. So this is material. So for example, if you're trying to build a battery, and I'm hoping that you guys will be able to do that, this is iron. This is a paper clip that you can take and make it into a wire that we probably will need down the road. I don't know if we're going to be able to do the motor or not. But the point being in here, this is iron. Iron resistivity is not this number, but it's actually 20 times the same thing, 10 to the negative 8. So if we're going to do iron, and we're going to use a paper clip, this is the resistivity of the iron. Now, the length is how long this wire is. So if I take a ruler now and measure how long it is, that is basically the length of this wire. As a matter of fact, this is up to this point if I'm going to make the connection here. So I have to use a ruler to find how big, how long is this wire. So that's L, okay? A is this area. It's a very tiny area. I don't know if you can see it or not, but it's the area of this wire. It's this area, the tip, which is very small. So you need calipers actually to measure how much the area is. Unfortunately, we're not in the lab. Otherwise, you will have a caliper that you do that, and it's going to give you how many millimeters the diameter of this one is. Then you use a formula for it, which is pi times the diameter over 2, the whole thing squared. And that is the area. So you have everything now. If you're using iron, you know its rho, you know its length. You can measure its length. You can measure its area. And you can find its resistance now in ohms. Okay, so this is not a hard thing to do. And then you compare the two. With a voltmeter, you have V. With an ammeter, you have I. And you can calculate R. And you can check, does this law work? You guys understand? Let's say, for example, V turned out to be 1.5 volt. 1.5 volt. And the current, let's say, for example, running through the battery, through the whole thing is 0. Let's say, for example, 1 amp. Then in this case, 1.5 divided by 0.01 is going to be 15 ohms. You check to see if it's 15 ohms or not with the calculation, and you're in business. So if it's 15 ohms, Ohm's law work. Now, it's very important, as I said before, to remember this relationship. When they are in series, when the trees are in series, the equivalent resistor is just the sum of the resistors, okay? When they're in parallel, it's the inverse of the equivalent that is the sum of the inverses. So this one, you have to find the sum of the inverses and you invert it back. The good new thing in here is that we're going to have a lot of these things. Hopefully you can guys have no problem with it. If you have difficulty, please let me know on how to do these calculations. Okay. So to go back to the original example, I have 3 ohms and 4 ohms from the previous example, of course. So the equivalent in this case will be 1 over R will be equal to 1 over 3 plus 1 over 4. The common denominator is 12, and 4 plus 3 is 7. Now, when I invert it, this is equivalent to 12 over 7. And so when I put, if this were a 3 ohms and this were 4 ohms, as if I don't have this at all, what I have in actuality is 12 over 7 ohms, and 12 over 7 is a little over 1. It's almost 2, actually. 12 over 7. Oops, it's 1.7, okay? It's 1.7 ohms. So as if I don't have a 3 and I don't have a, I have actually a 1.7. I have a 1.7 ohms. Again, I'm trying to put a point in here, okay? When things are in parallel, the equivalent resistor is less than the smallest one. In this case, the smallest one is a 3 of the 2. The equivalent resistance when they are in parallel is less than the 3. It's 1.7 actually. And in this case, if I add 3 plus 7, the sum is 7. 3 plus 4, I'm sorry, the sum is 7. In this situation, the equivalent resistance is bigger than the biggest of the two, which is 4 in this case. So that is one thing that you have to note about the about resistance and currents and things like that. Leave the objective for right now. Okay, we're going to jump right into the simulation and follow the instructions and basically do this activity. This is how it looks like, and follow this instruction. So what it says is the wire resistivity should be, I'm missing a B in here, small but not tiny. So the wire resistivity should be something small, okay, to simulate real wires in real life, okay? Because a wire like the one I had in my hand, like this wire, for example, that I use for my connections, has a finite resistance, actually. So it's not 0. But practically, in an ideal calculations, we usually put it 0. But to simulate a real situation, we're going to put the wire to have a small resistivity. The battery usually also have a resistance. So we're going to put that resistance to at least 1 ohm. So we need to follow this picture here. And then we're going to put an R1 here of 5 ohms. So we're going to put an R1 in here, 5 ohms. And we're going to put a rheostat in here. That is a resistance that you can change at will. We're going to put a battery in here pointing in this direction of 120 volts. And we will have a switch in here just to make sure that to turn it on time. We're going to put a voltmeter similar to the one I was showing you in this way. The red part of this voltmeter, remember I had a red and a black when I was showing that you guys. So this connection was red, this connection was black, and even the wires I have, they come actually color coded too. So that is really how. So even the wires, they come following that coloring too. So if we're doing this, I have wires that are black and I have wires that are red. So the black will be connected to the ground side of the voltmeter and the other one to the red one. And I'm going to connect them this way, okay? Meaning the red will be facing the cathode, the positive side of the battery. Is it? Yeah, I think, or the anode, I'm sorry. And then the negative will be facing the cathode, okay? One of them, the positive and negative. So anyway, the battery has a definite orientation. If you look at any battery that you buy, it has a positive and negative. The positive is always pointed with the long leg. The negative is always pointed with the short leg, okay? So if you want to do this experiment at home and having really batteries, this is how you connect the battery. You put the positive on one side, you put a rheostat resistance that can change so that you can play with its resistance. Okay, rheostat is something similar to this. Let me grab my kit in here. Okay, this is one. where I can basically move. Where is it in here? Why is it not moving? Yeah, I can move it in or out, okay? Depending on how far I move it, I can connect the wire in here and the wire in here, and the current will flow through only one portion of the resistance in this case, okay? So that is basically how I'm going to do it if I'm doing it in the lab, okay? If I don't have that, what I do in this case is I have a bunch of resistors, remove one, put another one, remove one, put another one, remove one, put another one until I complete it. And the table calls for at least 6 different values of this resistance, this rheostat. When you change it, you're going to read each time the voltage. So we're going to change the value of this thing in here. And each time you're going to read the current, how much current is flowing through the entire circuit. Okay. And how much voltage across this 5 ohm. You don't change the 5 ohm. You leave it as is. Okay. The second part of the lab is basically now you do the R2. You do the second resistor. You change the value to 10 ohms and you repeat the entire experiment with the 10 ohms. Okay. The third part in here, and I think I did not include the instruction, but I'm going to show you exactly how they are. Okay. No, I'm sorry. The second part is you do the 10 ohms. So we're in this step in here. The third part now is again vary this. So we put the second resistor and we fill this table, and we're going to do this one. So you guys should not worry. Now we are up to this point in here. The the numbers are off in here. So this should be. Please make this correction. So this should be number 4. This should be number 5. Okay. So step number 5 were there. And then finally, we do in series, then we do the whole thing in parallel. So I'm going to show you how the steps work and you fill out the tables. So let's do that. Let's connect that. Any questions? I'm hoping that you guys will correct these things in here. Please add that to the discussion so that you remember that, okay? So the thing is, on page 3 and page 4, make correction to the order of the bulleted points. We stop at 3, from 3 comes 4, and then 5, and then 6, okay? The numbers are shuffled back to 1 and 2. Does everybody understand this thing in here? Please make that and add it to the discussion so that I know that you guys are following the instructions. Yes? Okay, those who are watching the recording also later, please make the same corrections before you submit your discussion points, because I want to make sure that you also got this point in here, that the steps are a little bit went back to 1, 2, I don't know why. They should continue in this order, okay? So let's do this thing in here. Let's first of all click on these instructions, this link, and then do the instructions. So I just clicked on the link, and let me show you how that looks like from my end, which I'm hoping that you guys are doing it with me now. So your browser should open it. And here it is. Okay. This is how it looks like. So I'm going to click on the 5 and here it's fine. It's going to open the FET simulation. And don't do the intro, do the lab. Okay. And double click on it to open. Now you have it this way. So the first thing I'm going to do is click on the plus, click on this plus. If you like to keep it in this format, that's fine. I like it to be in this representation. It's the same thing. This is, I know they're trying to show you a battery and so on and so forth. But this is how we're going to do in here. We're going to switch to this one in here. I'm going to show the values. I'm going to need a voltmeter at some point, and I'm going to also need this ammeter for my experiment. So the first thing first is we need to do the circuit. Let me remind you how the circuit look like. So let me go and grab the instructions again. Here they are. And in the instructions, I'm going to basically need some wires need a battery. So I'm going to grab the battery first, and then the next thing is I'm going to have this resistor, and then this wires, and another resistor, and a switch. And at some point, I'm going to need an ammeter, and I'm going to need a voltmeter. So we need basically two resistors right now, a voltmeter, I mean a battery, where we set the value of the battery to 120 volts. It says specific to put it at a maximum of 120 volts, and the resistance R1 to be 5 ohms. And make sure the internal resistance is between 0 and 2. So in this case, it's taken 1, so we can take 1 if we like. Okay, you have no problem with that. And make sure the switch is closed to be, make sure the switch needs to be closed for the current. So we're going to close the switch at some point. So right now, when we grab the switch, it's going to be open. So let me stop sharing the screen. Let me go to my simulation in here. And here where we are. Okay. So I turned this used to be minus, so I made it plus. This same thing was a minus. And then I clicked on this one to simulate this thing. So I'm going to grab the battery. Since I clicked on show values, it's telling me this battery is, let me remove this electrons, okay? I'm gonna go with the conventional also, so that I see the current, okay? I don't want to have to see a bunch of plus electrons moving. I want to see the current moving the way that normally we talk in here, okay? I'm gonna double click on if you click on it, if you click on the the item, it's going to give you the option to change its value. So I'm going to put the maximum, which is 120 volts. That's what the lab instruction says. I'm going to grab a wire. It's clearly labeled wire. I'm going to put the wire in here. Okay. Once you snap in here, it's going to connect. If you don't like it, you have first of all click on it and click with the cut. Now the wire is not connected. So you need to connect it now, okay, to the battery. And after that, we have another resistor. So I'm going to grab any resistor in here. So it's not a light bulb, it's a resistor. And from one end, turn it around, okay? Once it's sitting vertically, I'm going to put it in here nicely, neatly. I'm going to grab another wire and also rotate the wire. Grab the wire, connect it to both ends of this. I noticed that it's not cleanly situated, so I'm just cleaning this thing in here. I'm going to grab another wire, connect it in here, and now I have completed this side. After that comes the other resistor. So I'm going to grab a wire, put it in here, and grab another resistor. This is a resistor, has to be 5 ohms. So I'm going to click on it. I'm going to change the value or enter it manually. Can I enter? No, I cannot. So I'm going to move around until I'm around 5 ohms. Then I'm going to move just one step to make it 5 ohms. So this is 5 ohms. So this is the R1. Then I have to have another wire in here and the switch. Here is my switch. It's clearly stated switch. Okay. Then a big wire. Okay. Let me bring my ammeter. Okay. I'm going to put the ammeter in here. Connect the two ends in here. Both of them are connected, by the way. I can tell by moving this thing in here. So the ammeter is in here. By the way, if you don't like something, you can either cut the connection, or you click on it, and one of the options is to delete. So that's if you make a mistake. Now I have my wire. Actually, I can connect it directly if I want to, but that's fine. I have extra wires. I have a bunch of wires, so there's no problem with it. Okay. And just to keep it neat and clean, so I'm going to move it closer to here, and now my circuit is closed. Okay. I have closed my circuit. Okay. At this point, I need my voltmeter. So I need to grab the voltmeter and put it right in here, put the positive side in here and the negative side in here, and it should read 0 volt. Because remember, V equals to Ri. I is equal to 0 right now. You guys see that? 0 amps going through the circuit. Because this guy is not closed. It's open. The switch is open. So when I close it, then the current starts to flow in this direction. Okay? And the current now should read something. So let's read the instructions to make sure that we didn't miss any point in here in the instructions. So we have everything right now, except we didn't close the switch. Switch is still open, okay? R1 is here, R2 is here. If we close it, so right now we have everything ready to go, okay? Oh, I'm sorry. Did we do this step in here for the internal battery resistance? So let me stop, make sure I do that because that's important. It's going to, so let's put a resistance in here of at least 1 ohm for the battery. So right now it's labeled 120 volts and 1 ohm internal resistor, just to simulate real situations, okay? So because real batteries have internal resistance, and wire should have a small, non-negligible, but small but negligible resistance. So we're in good shape now. Everything should be fine at this point. Did I miss anything? Please let me know from the instructions. No? So let's look now in terms of the R1 is 5 ohms, as we said. Click on the battery to fix it to at 120 volts. Click on the voltmeter, drag it in there. Click on the ammeter and do the same thing. Vary rheostat to obtain 6 different values in the table. Which 6 values you need? It doesn't matter, okay? So we're going to start with, let's say, for example, 5 ohms. And we go in increments of whatever we like, okay? So 3 ohms if you want to. So I'm going to stop sharing that screen and start sharing now this screen. So let's put the resistance now to about 5 ohms. Okay, 5.5, it's fine. Okay. I'm going to close the circuit now. So all I have to do is drag this leg, oops, and close it. Okay. Right now, it's telling me the switch is closed, it's fine. It's telling me the voltage is 48.64 and the ammeter is 9.73. So that's my data. So I'm going to come back into this and read this data into my table. So I'm going to put, does anybody remember what was the current? Anybody remember what the current value was? 9.73. So I'm going to put 9.73 here. Remember, the rheostat value, I don't care for it. Okay. And the voltage was 48 point something. So I'm going to put in here, go back into the 48.64. So please do not use these numbers, use your own, okay? 48.64. Okay. I have obtained one set of data for R1. What I'm going to do now is stop sharing the screen, go back to where my simulation is going, and change now the rheostat to a different value. Remember, I need 6 points, okay? So I'm going to click on this one and change the value in here. 11 is fine, or let's make it interesting. 12 and a half is fine. Now note the reading now. The current is gone to, it was 9 point something, now it's 6.21, and the voltage also dropped, 31.03. So again, 6.21. Where is the, where is my table? So stop sharing the screen. So I need to go into the table. So the current now is 6.21. And the voltage now is 31 point something. Let me check quickly. 31.03. Does everybody understand now how to complete this table? Because the next set of data, all I have to do now is basically, what happened to my, think I probably, yeah, here. The next set of data, basically all I have to do is change this number to anything in here, doesn't matter. Okay, 21.5 it is. Notice the current now is not flowing as fast as it was before. So the current drops to 4.23 and the voltage drops to 21.7. So that's my third point. The fourth point now, I'm gonna click on this one again and I'm gonna make it something. Okay, it doesn't matter what it is. So the current now slows down to 2.56 amps and the voltage now is 12.81. And the fifth point in here, or the sixth point, I don't remember, I lost count. Let's say, for example, 48.5 ohms. The voltage again dropped, the current dropped, and so on and so forth. Does everybody understand how to fill the first two columns?
Yes.
So I assume that now, by now, you can do all of this. Okay? Now the next two columns, they are identical. The only thing in here is, I'm gonna go back into the experiment and I'm gonna go back to a small value in here for the rheostat, okay? Okay, that's 5.5 is fine. I'm gonna open the switch in here. Can I open it? Yeah, it's open now. I'm gonna change, technically that's what we do. We have to close the switch and open the switch. We don't do the switch open. If we are in the lab, we have a disaster before our hands. You don't want to really keep it going. Usually you have to open and do measurement because there is another problem in practice. That's why simulations are no good. Is because in practice, what happened was the resistance starts to heat, and when it heats, its value changes. It's not the same. Okay, its value is absolutely not the same. So relationship, instead of being v equal to our eyes, linear function is going to change. It's not going to be linear, it's going to be non-linear. And you have the so-called non-omic resistor. So what you do in that case is you turn on the switch, you do the measurements with the voltmeter and the ammeter. Once you do the reading, you close the switch, you open the switch again, because you don't want the thing to overheat. You don't want it to heat at all. But in this case, you saw me changing the resistors at will, as if there is not a heating, and that is not true. Okay. So in the lab, and there is a question toward the end I need you to pay attention to, it's about this specific problem, because in practice, you run into that situation. In here, you don't run into, because of the fact that you're doing a simulation on a computer, which is honestly, it's like a game, that's all. Okay. But hopefully game that brings close enough to the idea that if we tomorrow they tell us, hey, physics 11, you can go and do your lab in class, you know what I'm talking about. You will see what that is. Okay. So I'm going to change now the resistors to 10. So this is R2 now. Okay. So now I have a 10 ohm. Okay. Leave this one to a smaller starting point. Now we're going to do the same data as before. We're going to close this. All you have to do is click on this thing, okay, to close it. Now it's closed, okay? Yes, it's closed. So now the voltage is actually went up to 69.22 volts, and the current is 6.92 amps, okay? I have a 10 amps, 10 ohms now. So again, for this one, I'm going to come in here and read 69.22 for the volts and 6.92 for the current. So I'm going to go back into the table. So let me stop this one and go back into. Oh, I'm sorry. Let's share that screen first. Share so that you guys see. So on here, I'm going to put 69.22. And the current actually is 6.92. Okay. I'm going to do the same thing again by changing the rheostat now. So I'm going to stop sharing this screen. I'm going to come in here. I'll share with you this circuit now. Technically, I did exactly the problem I shouldn't do. Technically, I should stop it, wait for it to make sure I don't let it warm and be too hot, and then change this resistor to something else. Okay. Okay. Now I have a different value for this resistor. I expect now the voltage to be less and the current to be less. So let's try that. Now it's reading 47.36 for the voltage and 4.74 amps. So I'm going to open the circuit again. But I know I will not forget, I will forget the numbers because I'm doing simulation and I am not taking my notes. Technically, I should right away quickly write what this value is, 47.36, and then the current is 4.74. Now, if I'm doing this lab, open the circuit again to make sure no current is running through it, stop sharing the screen, go back into my screen for the data and write it down as 47.36. 47.36 and this value at 4.74. Okay. I assume that you guys can finish this. Okay, and each time you change just the rheostat in this case. You don't do anything else, okay? You don't change anything else. You just change the rheostat. I know the lab tells you to remove the resistor and put another resistor, but that's the same thing, basically changing one of them, that's all. You guys understand what the next step is? So the next step in this column is change this value to another value and close the circuit, read the two values and put them in your table. So now I assume that you guys can complete these two tables. Please do not use my numbers, okay? These are not, if I see this one, I assume that you didn't do these two steps. So you're not gonna get full credit for this data cells. Please don't do that, okay? You guys understand now how to do R1 and R2?
Yes.
Okay, so I'm gonna go now, unless somebody else objects and needs more explanation, I'll be more than happy to share that with you. Now we're gonna come back in here and do the R equivalent when I have the two of them in series. So for that, I'm gonna share with you the screen again to put those two in series. So I'm gonna remove this voltmeter from here. I'm gonna push this one a little bit to this side. I'm gonna disconnect it from here. I'm gonna disconnect it from here and I'm gonna throw this one in the trash, okay? I'm gonna bring another resistor, okay? I can put it in here if you like and bring this to a side in here. Now I need to have one of them to be 5 ohms, so this needs to be 5 ohms. Okay, so I have one of them 5 ohms. Now this is in series, that means I have to read from the beginning of the first one and the ending of the last one. Remember, this resistance has to start small first. Something like 5 is good, okay? And then we're gonna increment it. So the rheostat is always the one that controls the whole experiment. So what we do in this case is we're going to close the circuit, leave 120 volts, everything else, and we're gonna repeat the same experiment, except now they're in series. Remember the trees? Now I have 5 trees and 10 trees, okay, in my analogy, and one after the other. So I should have about 15 trees basically altogether now if I'm doing it this way. So I'm gonna close the circuit now and read these two numbers. Technically, if I'm doing this in lab, my partner will say, okay, the current is 5.52 and the voltmeter is reading 82.74. Okay, we're done. So we'll close the switch now, open the switch, I'm sorry, and go stop sharing this screen and go to share this screen now and put my data here now. So the voltage is 82.74 and the current now is 5.52. Do you need, do you know what to expect next? So I'm going to stop sharing this screen. I'm going to come back in here, share with you this activity now. I'm going to change the rheostat now to any value, okay? I need 6 points again. So any value after that, no, make it too much big, okay? 16 is fine, okay? Now when I close it, I expect the voltage now, because there is a big drop now around the 16, so I expect the voltage to be less, and I expect the current to be less now. How much less is, here is how much less. 54.95, 54.95 for the voltage, and the current has dropped to 3.66 amps. So at this point, I'm gonna stop sharing, I'm gonna stop the circuit, stop sharing the screen, go back into my data where I'm putting my data in, and put the voltage. The voltage is 54.995, And oops, I did not write. 54.95. And the current is 3.66. Okay. Do you guys know how to finish this whole sequence now of things? You can add the other 4 basically for you guys. Yes or no?
Yes.
Okay. So basically we should have no difficulty with this part. Very good. So let's go back into here. Let me clean this table in here for me. Again, I don't want you guys to please do this thing, so it should be easy enough that you guys can do it. Let me show you the last part, which is a little bit of work, but we should be able to get the same thing. It's still no problem, okay? We should be able to do it. So let me stop sharing the screen. Let me go and share now this construction. Come in here. So again, I'm going to remove my voltmeter for right now for temporarily. I'm going to take this resistor. I'm going to disconnect it. Going to disconnect it in here. I'm going to move it up. Okay. I'm going to bring this one closer in here and connect this. Okay, undo. Can I remove this? I want to keep it separated. I want to keep the switch in here far away from this, guys. Okay. Bring this. More or less, they look like this. Okay. I'll close the circuit. Open the circuit. I'm sorry. And I want another wire, actually. 2 more wires. 3 more wires to be more specific. 1 wire connecting this ends and 1 wire connecting this ends. So now they're actually in series. I mean, they're in parallel. And bring another wire to complete the circuit. Okay. So now I have my circuit. Everything is fine. So now I need to connect. It doesn't matter if I connect it in here and I connect it in there or I connect it in here. It's the same point. As a matter of fact, I can connect it in here. Okay. This is the same point because it's the same voltage. All of these 3 points or 4 points are the same point. I'm going to connect it in here. These 3 points are also the same. When the switch is open like this one. When the switch is closed, actually, even all of these 3 points, all the way in here is the same point. Okay. So I'm going to leave it in here or here. It's the same thing. Okay. These 3 points are the same thing. For simplicity's case, I can put it in here. Now, the circuit element to whatever it is, I don't know what that's saying, but it's 0 volts, 0 amps. I need to go back to a smaller value again, starting point less than 10. Okay, 5.5 is good enough. I'm going to close the circuit. I'm going to read. I'm going to expect at this point a much higher current than even before, okay? Probably this is going to be the highest. Remember, the highest current so far I have seen was 9 amps. So probably now I'm going to see even higher than 9 amps from the previous experiments, okay? If this was the same resistance. Because this is equivalent to 1.7, actually. It's equivalent to less than both. Oh, I'm sorry, 1.7. This is equivalent to 1 over 5 plus 1 over 10. So it's equivalent to 10 over 3. This is equivalent to 3.3 ohms, okay, if we do the math calculations correctly. That is one of the things we want to find out. So we're going to close the circuit, and I expect this current to be higher, okay, than 9. It's 11. It's the highest current that we have seen today. Okay. Again, the voltage, I'm not seeing it because this writing in here was in the way. It's 37.64. It's less volt, and it's a huge current running through the whole thing now. 11.23. So again, I'm going to come back. Stop. Let me write down these numbers. 37.64 and 11.23 for my stuff in here. So I'm going to open the switch, stop sharing the screen, go back into my data sheet, share that. And now we're here. This is 37, at least my numbers, 37.64 and 11.23. You know what comes next, guys? Next, we change this value to any number between 10 and 20. 13 is good. At this point, we expect the voltage to be less than 37 and we expect the current to be less than 11.2, and we're going to report those numbers. So this is 6.6, and the voltage has dropped to 22.12. Okay, so that's basically what happened in here. So if we change this rheostat again to a different value, I expect everything to drop even more. This is 11.4, this is 3.4. If I change this one in here, each time I'm reporting the data on my table. So let me open the switch in here. Okay. This is the entire data collection process. Any questions about this? Is this good, the explanation that everything you can do it? Okay, good. So those are the steps. Basically, that's the numbers where hopefully you guys will put that in order. Okay, so now we're going to come back to the table and worry about the bottom. The bottom, you cannot do nothing about it unless you have everything filled in here. Okay, you have to fill everything in this tables. Once you do that, you're going to open the Excel file. So let me go back and open the Excel file, or at least download the Excel file, because I honestly don't know where it is right now. I mean, I can find it. It's actually in the lab, in your lab where I have them organized by class. So let me stop sharing that screen and come back to this screen. Okay, when you download it, and I'm glad I did this one, try to click on Enable Editing, because it will tell you that this file is protected and all of that, and it is protected because you want. So at this point, I'm going to have, this is identical to the previous lab. You can fill data in here, whatever it is. Okay, I don't know what the number was, 69 or 60 or something. Here it was like, I don't know, 9 or something like this. Okay, and I don't know, this was like 60. I don't remember how many. This was like 30 or something. This was like 6. I don't know. I'm just putting numbers. In here, it gives me the slope immediately. I need to fill everything in here to get the whole slope in here. Okay. Same thing in here. Once I fill out this 2 rows, it gives me the same slope. Once I fill out this 2 rows, it gives me the third slope. Once it gives me this one, it's going to give me the slope. And in the same time, it's going to give me plots in here. And the second plot right now, I have no data, so it doesn't show me any plot. So this is basically what I was telling you guys. You can either do the Excel file or you do your own calculation. If you do your own calculation, you have to find the difference between this one and that. This one minus that one. Let me go back to the PDF file to show you what I mean. In order to find the slope, you have to find the difference between this point and this point, and the difference between this point and this point, and you divide this difference by this one, and you do the difference between this one and this one and this one and this one, and also divide this difference by this difference. You do this now with this one and this one with this one, and you do all of these differences, calculations, and the ratios, and then you find the average of all of these ratios. That's going to be here. Same thing in here. This, you subtract from it this, you subtract from it this, and you divide both of them, and you have one value. This, you subtract from it this, you subtract from it this, and now you have a second value. Now this minus this minus this, and you divide both of them, and you'll have a third ratio. This minus this one, this minus this one, and you divide both of them, and you have the fourth ratio. This minus this one, this minus this one, divide by one, this one over this one, you're going to get the fifth ratio. Once you do that, you should be able to find the average of these 5 values. They should match what this slope is. Okay. You do the same thing in here. You do the same thing in here. Okay. Or you do the Excel file. It's up to you guys. Please tell me which one you're doing. Are you doing in the discussion, you tell me, I looked at it, and I'm going to do the Excel file, or you're going to do the calculations. Now, if you do not do the Excel calculations, you have to include the graphs, these graphs. You have to do them manually. In other words, you plot in the x-axis the current I from here, this current, And the y-axis, you plot this voltage, and you connect the dots. Okay. And you do the same thing for R2. Okay, that is all required. Okay, that is what is required. This is not required. Okay, that is what you will get from this one in here. Okay, so now that's it. That's all there is to it in terms of your data. Then we have a bunch of questions now. You're gonna find this R1 is supposed to be 5 ohms. R2 is supposed to be 10 ohms. This slope should be close from 5. This should be close from 10. Okay, so what you do in this case is you take this slope, whatever that value is, minus 5, and you divide it by 5, and you multiply by 100. Don't forget to take it in absolute value. And you tell me, is the error less than 5% or not? Okay, if the error is more than 5%, something went wrong. You need to fix it. Okay, because I know this slab should be very accurate. You do the same thing for both R1 and R2, by the way. Then you do the slope here, minus 10, divided by 10 times 100, and the error for R2. Both errors should be less than 5%. If one of them is higher than 5%, something went wrong completely and it's no good. You need to go back and check your configuration, and maybe you didn't collect the data right or something like that. Okay. Now, this slope must be equal to the sum of these two slopes. Okay. This slope must be equal to, the inverse of this one must be equal to the sum of these two inverses to check whether or not these rules apply. No, I'm sorry, verify Ohm's rule, Ohm's law, it will be verified. I'm sorry, let me, I took a step before. This is Ohm's law. So what you're saying in here, if the error is less than 5%, it should be accurate. Ohm's law should work. That means this voltage is equal to this I times this slope, okay? And it should have a zero y-intercept. Okay, if it has no zero y-intercept, that's what the errors are coming from. In other words, is it close enough from V equal to Ri? If it is, you're going to state it in here that Ohm's law works. Okay. So we have the graphs now. Either you do the graphs manually or you do the graphs following the Excel spreadsheet. That's your options. This is not required. Okay. For other classes, I require it, but for this one, because we have a lot of things to do. So do the best to fit your lines, pass through, do the best fit lines, pass through the origin. When you go through the Excel spreadsheet, you're going to find the lines and you're going to look at them and see, do they pass by the origin? If they don't pass by the origin, that is an error. That means it's not something you can do anything about it. That means Ohm's law is not really exactly accurate at this point. There are some wires that are not accounted for or some stuff like that that can need to correct for it. Now, calculate the slopes. Now, we're going to take R1, which is from the slope, from this value. So R1 is exactly this value, whatever we ended up in here, whatever you type in here. Remember, you're going to type this one manually in here. Okay. Coming from the Excel spreadsheet, that is. Spreadsheet will give you that, or you calculate it manually. It doesn't matter. So you're going to put it in here. And then it's 5 ohms from the instructions. They tell you to put 5 ohms, okay? And the error that you calculated from the previous step. This error for R1. Then you're going to do the same thing for R2. R2 from the slope. And from the value, it's supposed to be 10 ohms. And the error in percentage, okay, the one that you calculated from the previous question, R equivalent. R equivalent from the slope is this one for the series. This is R equivalent from the series, from the slope. So you plug in that number here. And this should be 15 because 10 plus 5 should be 15, okay? from the experiment. Again, you're going to find the difference between them and is it acceptable? Less than 1%. Now you do the R equivalent for the parallel. For the parallel, it's coming from this slope, the last slope basically that you have in the here. And you're going to copy that number and put it in here. Sorry, did I skip this table? Here, okay. So these slopes, they will be translated in here. This should be 1 over 10 plus 1 over 5, 1 over 10 plus 1 over 5, inverted. The whole thing is inverted, okay? So this should be 10 over 3, and 10 over 3 is 3.33, okay? Here, it should be 3.33 ohms, okay? Whereas in here, it's the slope, whatever that slope is. So this should be close from 3.33. Again, you use the same formula to find the percentage error, okay? Question 4. What is the difference between an ohmic resistor and a non-ohmic resistor? An ohmic resistor obeys Ohm's law, namely V equal to Ri. A non-ohmic resistor is non-linear. It's not a line anymore. You see those curves that you're going to get? They should be lines, all of them, okay? In actual lab, that is not exactly true. If you wait for it a long time and it's going to heat, it's going to not be actually a line. It's going to start to behave not as a line. So that is the difference between them. The difference between an ohmic resistor and a non-ohmic resistor is that an ohmic resistor obeys Ohm's law. In a sense, it's a linear relationship. Does this make sense to you guys? We would do this if we are in face. I mean, if we are face to face. Unfortunately, we are online, so the only thing you're going to see is an ohmic resistor. I mean, we can simulate it honestly and do a timer, and if that timer exceeds so and so, it's going to decrease it by such and such. I mean, increase the resistor by such and such by such and such, and you will see the behavior nonlinear. But for this simulation, it's not done. You guys understand the difference or not? Yes or no? Okay, V is good with it. Samantha is good with it. About the others? Sharon, Amanda, Yuan-Tian, Victor.
Yes, I'm good.
The other Amanda. Okay, good. So that is basically what this thing's saying. Okay. And then analyze table 2 and determine if errors justify non-ohmic resistance for either of the resistors in the circuit. You should not have non-ohmic resistors. They all should be fine, okay? If you do, please let me know. And then the conclusion. Before you do the conclusion, at this point, basically what you're doing in here, you're checking Ohm's law, actually V equal to Ri, and you're also checking the series and parallel circuits. Okay, and whether or not the formulas that you have work or not. This is your lab. Again, if you choose to stay, I'm going to stop the recording unless somebody has a question. If you choose to stay until 9:10, I'm going to switch my headset for that, the one that I can move around with. And if you have any question, please do not type it. You have to speak it out because I will not be next to the screen. And give me a second or two so that I can rush to the chair and basically turn on the speaker and answer the question that you have. Yes, if you choose to go because you have other things to do, because you know what you're doing, that's fine too. Good?
Okay.
Okay, so I'm going to stop the recording.